Hi everyone, my name is Kumaran, and in this presentation, I'll talk about adaptive caching for faster video generation with diffusion transformers. In this work, we look into accelerating video generation because high quality video generation is slow. And retraining these video generation models, for instance, with distillation to make them faster is also expensive, both in terms of data and computations. As an alternative, here we introduce adaptive caching, an effective training-free accelerator for DiTs. We show that adaptive caching is stable even at lower latencies. Here we compare with a prior state-of-the-art PEB, and it also shows fewer visual artifacts. It's preferred among users, and it's also compatible with multi-GPU settings, so the speedups can be improved even further. So we base this work on the observation that not all videos are created equal, meaning each video generation is unique. Some videos may have homogeneous textures or simpler motion, whereas others may have high-frequency textures or complex motion. To validate this more formally, we first look into how much computations each video generation need. And we see that when reducing the number of denoising steps, not all videos break the same, meaning each video requires a unique amount of computations to generate at a reasonable quality. We also look at how redundant the computations are among subsequent denoising steps. We see that the feature similarity, although it follows a common trend, it's actually unique to each video generation. Meaning, if we are to reuse some of these computations across multiple steps, it better be content dependent. So we ask the question whether we can exploit this content dependency to optimize the quality latency trade-off. We introduce adaptive caching. So the basic idea here is to control the number of computations depending on the video being generated. So here we have a baseline with 100 denoising steps. And if we apply adaptive caching on top of that, we can achieve on average a 4.7 times speed up. But if you look at the number of steps, it actually is unique to each video. So if we look at this in more detail, here I'm showing a DIT unrolled across diffusion steps. And in adaptive caching, we decide to cache and reuse previous representations for some of these blocks. We do this by estimating the rate of change between the representations. And if the rate of change is high, which means we can't afford to reuse the representations for a longer period. By caching or computing, what I mean here are the residual computations, such as spatiotemporal attention, cross-attention, or MLP, which account for most of the computations. So once we have this distance metric, we can select an appropriate caching rate from a predefined codebook. This codebook can be tuned with a small set of calibration videos. So once we have this caching rate, up until we meet that point, we decide to reuse the previous computed representations. Up until this point, our contributions are not video specific. This can be applied even for image generation. To benefit from video information even further, we introduce motion regularization. So if you look at the motion regularization in detail, the basic idea here is to regularize the caching rate based on motion, which means if we have a high motion, we can't afford to cache for a longer period. We do this by estimating a latent motion score based on frame differences. However, we realize that the latents can be noisy, particularly at the start of denoising, and hence the motion score can be unreliable. So if you look at this high moving sequence, the values in blue, which shows the motion score, is small at the start of denoising. To alleviate this issue, we compute a motion gradient across the denoising axis, which can be used as an early predictor to an accurate motion that appears later in denoising. So when we add up this motion score and motion gradient, it acts as a reliable predictor of motion. Finally, we use this motion score as a multiplier on our distance metric to increase the metric and reduce the number of caching steps. All right, so if we look at some quantitative results, we see that adaptive caching shows best speedups among training free DIT acceleration methods. And it generalizes across different baselines. Here we show some qualitative results, which shows that adaptive caching has fewer artifacts compared to prior state-of-the-art. And we also show that motion regularization definitely helps improve the generation quality. And we see fewer artifacts, both motion and visual, when we have the motion regularization. Finally, we show that it can generalize across different spatiotemporal resolutions. And we can control the speed up of adaptive caching by using different basis cache rates in our codebook. If you have any questions, please drop by our poster on Wednesday, and you can see more video results on the project page. Thank you.